So, in order to do this, let's consider this space. We will consider the configuration space, the n configuration space of the complex. The n configuration space of the complex is the set of x1, x2 till xn, endpoints in the complex, such that xi is different from xj. Okay? We have n distinct points in the complex. No? So you have the complex, you can take it as it, and you have like n different points over there, right? But this space can also be thought as the complex, right? Taking out Hij, where Hij will be this is Cn, yes, such that xi is equal to xj, right? We are taking out the diagonals. These are hyperplanes, right? These are hyperplanes. And so, okay, let's see how this looks, no? For example, I think the only example that I could try to draw in the tree space, but let's just draw it in R2, no? This is C, and we are just taking out the diagonal, no? Like this. And here, we can interchange these two spaces, right? We can always, each hyperplane is dividing, no? The space in two parts, the right part, the positive part, and the negative part, right? And then we have an action of the symmetric group on this space, right? So the symmetric group is acting on the configuration space and it's just changing the complement, right? It is interchanging this part. So the space of orbits, I will put it like this. The unordered configuration space, this is the ordered configuration space on C, will be the space of orbits, right? Like configuration space, the quotient by the action of Sn. And something amazing passes. What happens is that the fundamental group of the configuration space will be called, I will put it like this, the Pn, and this, the unordered, I'll put it here. Is the braid group. So I know that many of you say that you don't know what is the fundamental group, so I will tell you what is the fundamental group, and you will see why it is so impressive, right? So, the fundamental group, P1, the fundamental group, take X and a space with a base set point. So you take you take, for example, I don't know. The torus. Okay. Have everybody heard about the Jordan curve? The Jordan curve theorem? Yes? The Jordan curve theorem that says that any closed simple curve in the plane contains two parts, inside and outside, right? This is funny because it's the example that I always use to introduce the fundamental group. So, yes, I still have time. So, this is the trick. This is an exercise to do right now, no? Because to those that haven't worked with fundamental group, this is an easy, this is an amusing exercise, okay? So, the Jordan curve theorem tells you, if you draw a simple closed curve in the plane, it always have an inside and an outside, right? And this is like really cultural because in many places they say you are in or you are out, right? And so in this case, we will see that this I don't know, okay. So you have an inside and you have an outside. My question is, you take a surface. Imagine the surface that you wish, no? The question is, the Jordan curve theorem is always valid in any place? Meaning, imagine whatever you want and draw a simple closed curve. Does it always have an inside and an outside? Yes or no? What do you say? Just think about it 2 minutes. Just make some drawings in your notebooks if you know the answer or you don't know the answer. Try to imagine a space or a curve that doesn't divide the space in two parts, inside and outside. Can it be done or can it not be done? What do you think? So I will just turn around and I will write some things until you think. No? 2 minutes and okay. Okay. I don't know if a minute has passed, but what do you think? So let's do votation. So can we draw a circle that has inside, that have no inside or nor outside? What do you think? Yes? Can we draw a circle with no inside and no outside? Yes or no? Well, for yes, raise your hand. And for no, raise your hand. You say that we cannot draw a circle with inside and outside. meaning that every circle, each time that we draw a circle, it has an inside and it has an outside, every time, right? So that's the assertion. In any surface, whenever we have a surface, whenever we draw a circle, it has an inside and it has an outside. Because if not, Jordan was crazy, right? No? Yes? Okay. So, in fact, this was one of the main discoveries of the last century, right? It turns out that there are many special circles, right? That in fact, if we study circles, we can identify surfaces. We can classify surfaces by the circles that lives in them, okay? And how does this work? For example, think on the torus. Think on a donut, the outside part of a donut, right? If you think on the outside part of the donut, then when you cut along this, what do you get? You get something like this, right? Because you are cutting this curve will represent this and this, no? Each time that you cut, your curve becomes two curves, right? So, but here you only have one part. So this cannot be outside and inside at the same time. So this curve is special. It's nice, right? It's amazing. So now we have these special curves that have no inside and no outside. No? These are good curves. We call them essential. Because the other ones, the curves that have an inside and an outside, then we could contract everything to the inside, right? We could do, remember, we are looking like with our topologist eyes, right? And as we are topologists, we like to deform things and to do like, right? And then we can take this circle and then begin to shrink it, and make it just 1 point. But maybe 1 point is not interesting enough, no? Because it is just like, poop, right? And so, okay, so these curves are not interesting by themselves because we can, it's the same that happens when we have a bigon, for example, no? If we have a bigon, boom, 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 and we can contract all of this to the same curve, right? We are saying that these two curves are equivalent by making like an homotopy. Now I'm telling you words, right? Homotopy. And then we can say that we have an homotopy. If we can deform, we can take this curve to the other curve. And curves are defined by homotopy, that in certain sense are simple curves, no? Or not essential curves, okay? This is nice, right? So, we have this curve here, and just to finish with this example, because it's a nice example, the aim in a surface or in a general space is to find all the sectional curves, no? To find all the essential curves, no? And you will say like, oh my God, that will be like a lot of curves, no? That would be like a million or trillions or infinite number of curves, right? But we have algebra. And then we will use algebra to encode all of these curves. And how we will do it, just look at this. Well, we have this curve, but let's say that here I have a distinguished point, no? I will say that it is a market point. And then I will begin to look for all the curves that begin and ends in this point. So I have this curve, and this curve, this becomes this, and I will look for all the curves that begin and ends in this point. I have this, and I know when I cut along it, I get a cylinder. But then afterwards, I can look in the cylinder to another essential curve, right? But remembering that I must begin here and end here. It doesn't matter the combination, because all these 2 points represent the same point in our original space, right? So when I am in the cylinder, I will cut along this other one, like boom, 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 boom. And when I cut along this, then what do I have? Then I will have I will put this A, B, this is A, and this is B, right? So I will have like this, A, B, B. A, B. And now I can see my donut, I can see my torus splitted, identified as a square, right? Yes? But this square is already on the plane. And in the plane, Jordan was right. No? So in the plane, any simple closed curve has an inside and has an outside, and so it is simple curve. It is like, it's trivial, right? It doesn't matter. So these 2 curves are enough to represent all the curves over there. Nice, right? But we say that we need an algebraic structure, right? So with this, I hope that when we repeat this, I will, just to finish this argument and this idea on the fundamental group, is when we use this idea, you take your favorite surface, and then we will become hunters of essential curves. No? You find an essential curve, and you cut along it. No? And then you get a new surface when you cut along it. And then you find a new essential curve, and you cut along it. And then you will get another surface. And then you cut, and you cut, and you cut, and you cut. And when you arrive to a disk, or to a union of disk, you have all the generators, and the number of curves that you have found will give you exactly what surface it is. It is a complete characterization of the surface that you get. Surfaces are characterized in this way. It's beautiful, right? Well, for me, it's beautiful. The first time I saw it, I was like, wow, okay. But, okay, this is algebraic topology, no? This is why it is so amazing, so amusing, right? So, we have this. And this is why curves, simple closed curves are important, right? And the fundamental group of a space, it encodes exactly that. It takes all the curves. You fix a market point in your space, okay? You fix a market point in your space, and then you look to all the simple closed, all the simple closed curves. Okay? You look to all the simple, to all the closed curves, okay? That is meaning like all the circles in the surface or in the space, okay? And up to homotopy, because we are topologists, okay? So, and this is the fundamental group. But I say that it is a group, so it must have an operation, right? And the operation is by concatenation, meaning you give a term, return to the starting point, and then you begin with the other curve, right? It's quite natural. Okay? So far, so good? Yeah? Okay. So this is the fundamental group. Okay. So Fadel and Evitz in the 70s. Everybody can see this? They prove this, that P1 of the unordered configuration space of C is the braid group and of the configuration space of C is Pn. And what does this mean? Okay, this means the following. We take endpoints. Well, I will do it in two ways. You take endpoints. These are distinct points in the complex plane, and you think on a curve, on a closed curve, it will mean that you take this point and you begin to move it, and at the end it has to return to itself, right? The same goes for the next one. No, it will have to do something like this, and this might do something like this, etc. No, so when you look at this in this way, it looks messy, right? And besides, you can say like, oh, but they are intersecting over there. But we have time, no? We have time. So when we have time, so we begin here, and then we might do something like this, and then we return to the same point, right? And then we go here, and then we go over here, we go here, and then we arrive to the same point. Okay? As you can see, in each section, we will need to have 4 different points in each section. And then we will recover a braid, no? But this is a special braid because it is the point 1 is beginning in the point 1, the point 1 is ending, the string 1 is beginning in the point 1 and ending in the point 1, right? The same for the second. The second string is beginning in the second point and ending in the second point. But remember that we have an action of the symmetric group on this, right? So when we begin and end in the same point, this will be called the pure group, braid group, okay? Meaning that you have no permutation. And when we have the unordered, then all these points, you can begin in any of them and end in any other, no? Because they are unordered. They are only considered as points, right? It makes sense, right? So that's why the complete group is the Vn, but only when we consider the unordered configuration space, and when we consider the ordered configuration space, then we get the pure braid group. Okay, and these are the braids. And with braids, we can study knots, for example. Everybody has heard about knots, knot theory, like, yes? So with braids, we can from this, we can pass to study knots, no? Because there is this famous theorem that is called Alexander, that says that there is a function from the braids, from the tower of braids to links, right? Meaning that if you have a braid here, you can close it. You can join the first one with the first one. You can join this one like this, and then you get a link, right? And so with this, you can construct plus the theorem of Markov. No? This implies not invariance, no? And this has been done by Jones and many others, no? Okay. I work a little with that, so if you are interested. Okay. So this is the general framework of this. And as you can see, now we can rely braids, no? That were this abstract group when we take out this relation with these spaces. Because at the beginning, we have a group generated by reflections. We have a space, we have reflections. And then we complexify it, no? We take the complement of it. We took the complement of it, and then we consider the fundamental group, and with this, we got the braid group. And the presentation of that group, it was the same one that we have originally generated by reflections, but only taking out the relation, the involutions. So, I would like to make my statement a little more precise. Can I erase this? I really want to keep that. Yes, can I erase this? Okay. So let's see. Okay. How can we generalize this? No? How can we pass from this example to a more general framework? Okay. So I will need to give you two definitions. Okay. First, let A and B, well, let S and T, two abstract symbols. Letters, if you want. And then we will define the word P, S, T, M as I will put ST M over 2 if M is pair and ST M S if M is odd. This is just a fancy way to say that we have ST, etc. No? And we have here exactly M letters. Okay? Okay. The second definition is the following. Let S be a finite set. A Coxeter matrix on S is a symmetric matrix MST, oh, sorry. MST with ST in S. I already said that it is symmetric such that MSS equals to 1 and MST it's a natural number or the infinite. Okay? So to any symmetric to any Coxeter matrix, we can associate what is called a Coxeter graph. A Coxeter graph, no? And the Coxeter graph, I will put it like this: gamma sub m. That is, it will be the vertices of gamma will be exactly S, the set S, right? And we will say we have S and we have T. We will say that there is no edge between S and T if MST is equal to 2. We will put a simple edge if MST equals to 3. And in all the other cases, we will label it. Okay? And so, with this, can I erase this? Yes? With this in mind, now we will define our study of object of the whole course. So, brace yourselves, okay? So, the Artin group of gamma, we can put gamma because we can, as you can see, we can recover, if we have a Coxeter graph, we can recover the Coxeter matrix, and if we have the Coxeter matrix, we can associate the Coxeter graph, right? So, I will just put gamma. The Artin group of gamma will be the group generated by S, no? That are the vertices, and we will have the following relations. We will have ST, MST equal to P, TS, MTS, no? And we know already that this and this is the same because it is a symmetric matrix, right? And whenever MST is different of infinity. So this is an abstract group, right? This is only given by presentation. You will say like, what a random group, right? It is just given by a presentation. Okay, and of course, the Coxeter group, this is by definition, okay? And the Coxeter group associated to gamma will be the Artin group modulo, or just adding the relation S squared. Meaning that it will have exactly the same presentation as the Artin group, but with the involutions. That is exactly the case that we have here, no? We have the braid group, we have the braid relation, but we are just adding the involution, the reflection. Okay?
In the odd case, you want to, for the relation, it's n plus 1 over 2 or n minus 1? In the odd.
Ah, yes. Yes. Here it must be k.
K.
K, yes, k. Thank you. Yes. Yes. So let's see a couple of examples. So let's consider the simplest will be like this, no? No, it's not true. The simplest will be just like this, no? and just like this, no? If we put S, W, the first gamma, no? Who will be W of gamma in this case? Will be Z2, right? And the Artin of gamma will be Z, the integers, okay? If I put just two vertices like that, what do I have? When I consider the Coxeter group, what it will be? It will be, let's put this S and let's put this T. I will write the presentation, the whole presentation. So it will be S T, S squared, T squared equals to 1. And then we said that with 2 it will be here, no? If there is no H, then MST is equal to 2, so it will be ST equals to 2S, right? Which group is this? Sorry? Sorry? Rainfall?
The Klein group.
The Klein group. Not exactly, no, because it is the direct product of. Yes, it is. It is 1, of course. And if we consider A of gamma, then we only take out this, and then it will be Z cross Z, right? Okay. So as you can see, we can go from direct products. We have direct products, but we can also have like this, no? Here we can have an infinity, no? Here I can have an infinity, so W of gamma will be ST S squared 3 squared equals 1. And just like that. And this will be the free product, right? This will be just the free product. And when we pass to Artin, it will be the free product of Z with Z. So this is a nice example because you can see that we can have a whole variety, no, of groups. We can go from free abelian groups to free groups. And these are quite different, no? There is a lot of families of groups among them, no? And of course, the example that we want to study, no? The main examples that motivate all of this, no? So what happens if I take 1, 2, here I have with 3, no? And here I put A and B, then it will be the Coxeter group of this, no? Is AB, A squared equals B squared equals 1, and ABA equals BAB. It's okay, no? And, and when we pass to the Artin, it will be AB, ABA equals BAB, no? So in this case, we have S3, and here we have Bn. Okay, and in the general, no, when we consider this graph, when we consider this graph, what happens? How is the presentation here? This graph has a name. This is called AN minus 1. And so when we consider this, then we have AN minus 1. We'll have the presentation T1 till Tn minus 1. If they are consecutive, they have the braid relation, right? Because we have a 3. 1, 2, it will be 1, 2, 1, 2, 1, 2, right? 2, 3, 2, 3, 2, 1, 3, 2, 3, no? So it will be like Ti plus 1, Ti equals to Ti plus 1, Ti plus 1, okay? Then Tij equals Tj, Ti. And this is if I plus minus j it's greater or equal than 2. And this corresponds to this, no? Between 1 and 3, there is no edge, right? So they commute, right? The same 1 and 4, because they are long, they are far from one from the other, right? We don't have edges among them, so they commute. And there is all the relations that we have, no? And we don't have infinity. And of course, the final relation is all of them are involutions, right? So, and then for this graph, we have the symmetric group. We have the symmetric group. Okay? And when we pass to the Artin group, then we will have the braid group, as we already saw. Okay? So, just to finish with this example, what happened? Because as you can see, this is completely combinatorial, right? Here I'm not saying any geometry. Here I'm not putting any geometry. Just a combinatorial set of tools. These are words, these are letters. But we began with geometry. So how can we pass from this to geometry? Because at the beginning, like, even for this case, how can we interpret this Coxeter group by means of reflections, right? And the answer, at least for this case, will be as follows. Okay, consider the symmetrical, the symmetrical group, right? For the symmetrical group, this is S3, right? This model works for S3. So, because we have 3 vertices. These are our 3 vertices that we have. No? So for S4, we have this, but then we will add a new vertex. No? And then we will have the tetrahedra. And now the generators will be the ones that correspond by cutting. We will take the reflections that cut the simplex. This simplex can be, we can look at it in R3, right? And we can look at it as, we have R3 here. And then, how can we look at it in this space? We can take we take out all the hyperplanes, as we did before. And I cannot draw it. I cannot draw it right now. But the point is, we will have in here, we have this. There will be these three mirrors. We will have these three mirrors. This will be A, B, and C. And look at the angles that they form among each other. Here, we have three mirrors, so between A and B, between A and C, there will be a 3. And let me just number it better. And then I will have A, B, C, like this. Yes, this is better. So if we count the number of mirrors that passes through in the intersection of A and B, there are 1, 2, 3 mirrors, right? Yes? So we have A, B. The number of mirrors that passes through A and B are 3. So it will have these 3. The number of mirrors that passes between B and C, there are also 3, because it's this one, and this one, right? It's also 3. So B and C, it's also 3. And between A and C, there are only 2. Okay? Between A and C, there are 2. But we say that when we have 2, we don't draw the edge, right? And when we have 3, we don't put the. So this is the Coxeter graph of the symmetries of this polyhedra. And so we can recover the presentation or the interpretation of the symmetric group, that it was a completely abstract presentation via a geometric representation. And the braid group, in this case, it will correspond exactly to the, I erased already what it was the configuration spaces. It will correspond to the configuration spaces, no? That meaning that we have the complement of these hyperplanes, of the hyperplanes that cut our polyhedra, okay? And then we complexify and we consider the fundamental group. And that's the way we recover the Artin group, okay? And well, that's the introduction of Coxeter and Artin groups. Tomorrow, I will tell you what is the KP1 conjecture, okay? And I think I will stop there. Thank you.
Thank you.